This is week 5 problem solving session 5. I'm your TA Sachin from the Indian Institute of Science, and today's topics are coding of sources with memory and channel capacity. As usual, we'll solve 10 multiple choice questions which have a similar pattern to the assignment questions that you have received this week. The first question is: consider the binary Markov source with memory mu equals 1 and output alphabet A comma B, having the following state transition diagram. Transition probability from A to B is 0.6. The output symbol is B. From A to A is 0.4. Output symbol is A. And from B to A transition probability is 1 with output symbol A. On each branch, the transition probability is indicated together with so in parentheses they have given the output symbol emitted by the source when the transition is made. What is the entropy rate of the given Markov source? the stationary probability distribution of the states of this Markov source can be written as the probability that you go to state A at time t plus 1 is zero point 0.4 times so since this is a Markov process, um, the state transition matrix for this Markov process is uh, so since you go from A to A with probability 0.4 and from B to A with probability 1, first row is 0.41 and from B to B probability is 0 and from A to B probability is zero point 0.6. So that's the what do you call it? Transition matrix. So that's the transition matrix. So from the transition matrix, we find the stationary distribution by solving pi tilde times, call this p pi tilde times p is pi tilde. So that is p of A, p of B is 0.41, 0.60 times p of A, p of B. Sorry. Uh, p of A, p of B times 0.41, 0.60 is p of A times p of A, p of B. So that will give you Just give me a minute. I'll be back. I'm back. Okay. So we have the transition matrix for the Markov source. No, I can't hear you. Here's the question. There's a binary Markov source with memory mu is equal to 1, and the uh, Markov chain is transition diagram is given below. So the output alphabet has two. Let me write the solution though for other people. So from this, we have to solve for the stationary probability, writing P of A, P of B is 0.41, 0.60 times P of A, P of B, which means P of B is, so those equations, you'll get two equations, P of A is zero point 0.4 P of A plus P of B. That's from this row, and the second row is P of B is zero point 0.6 P of A, but there this equation is also the same thing. P of B is zero point 0.6 P of A. But we also know that P of A plus P of B is 1. So this gives you the stationary probability PFA PFB is 5 over 8, 3 over 8, and that gives you the entropy rate is h of u2 given u1 equals a into pu of a plus h of u2 given u1 equals b, pu of b is 5 by 8, h of zero point 0.6 plus 3 by 8 f0, which is 5 by 8 times 0.971, approximately 0.61. Question 2 is Z channel with crossover probability epsilon equals 0.3 is given as 0 goes to 0 with priority 1, 1 goes to 0 with priority epsilon, and 1 goes to 1 with priority 1 minus epsilon. That's a Z channel. What is the capacity of this channel? Capacity is the max overall priority distributions over X of h of y minus h of y given X. If let P1 be equal to probability that X is equal to 1, the probability that X is equal to 0 is 1 minus P1. H of y given X is h of y given X equals 0, the probability of X equals 0 plus h of y given X equals 1 into probability that X equals 1. H of y given X equals 0 is 0, because if X equals 0, then y is equal to 0 with probability 1. 0 into 1 minus P1 plus h of y given X equals 1. So given X equals 1, uh, probability that y equals 0 given X equals 1 is epsilon, and probability that y equals 1 given X equals 1 is 1 minus epsilon. So The entropy h of y given x equals 1 is the binary entropy of epsilon, and probability that x equals 1 is p1. H of y given x is therefore p1 times h of epsilon. To make it binary, I'll write it as h2 of epsilon. Then h of y, h of y will be h2 of 1 minus epsilon times p1. From that we'll get I of xy is h2 of 1 minus epsilon times p1 minus p1 times h2 of epsilon. To maximize ixy with respect to p1. Since it's a binary input, the distribution is given just by p1. Probability p1 also, once it is fixed, it also fixes the probability that x is equal to 0. So we just differentiate I of xy with respect to p1. You get, so for the second term, h2 of epsilon is fixed. Uh, h2 of epsilon times dp1 by p1 is just 1, so second term becomes minus h2 of epsilon. First term, you have to differentiate h2 of 1 minus epsilon times p1. Well, I'll let you do the math. H2 of 1 minus epsilon p1 is just the binary entropy function with parameter 1 minus epsilon times p1. You differentiate that with p1, and you should get 1 minus epsilon times log of 1 minus epsilon p1 divided by 1 minus epsilon times P1. So this entire thing is in the log. And equating this to 0, you'll get P1 should be 1 over 1 minus epsilon divided by 1 plus 2 power h2 of epsilon divided by 1 minus epsilon, which is approximately equal to 0.421. So epsilon is zero point 0.3 here. So we have to substitute that and substitute for h2 of zero point 0.3, from which you will get P1 is approximately 0.421. So this value of P1 maximizes your capacity, which is I of xy. So the capacity is, substitute P1 equals 0.421 in the capacity expression, that is h2 into 1 minus epsilon P1 minus P1 h2 epsilon. And you will end up with capacity approximately 0.5 bits. So all the intermediate mathematical steps are left to you. I'm only giving the method to solve the problem. Finding the uh, differentiating with respect to P1, then substituting the value of epsilon to find P1, and then substituting back the value of P1 and epsilon to find IXY. All that is left to you. Question 3. Consider the Z channel with crossover probability epsilon is equal to 0.3 of question 2. What should be the input distribution that maximizes the capacity? So we already solved it in the previous question. From solution to Q2, capacity was maximum when P1 is approximately 0.421. So the distribution is probability that x is equal to 1 is P1 is 0.421. Probability that x is equal to 0 is 1 minus probability that x is equal to 1 is 1 minus 0.421, and that is what? 0.579. So that's the distribution. Question 4. Find B2 inverse of 0, 0, 1, 1, 1 101100, where B2 of n is alias code 2 for positive numbers. Alias2 code, uh, what do we do in alias2 code? So the number of zeros before the leading one is coded using the alias1 code, and then we remove the leading one in the binary number in alias2 code. So here the initial part of 001111, this number is alias1 code. So first we see the number of leading runs of zeros. So we have leading runs of zeros is 2. That's why you have to, right? We have to look at the next 3 bits. And that will give you the length of the number. Next 3 bits to find the length of the number. So next 3 bits are, for 111 is equal to 7 is the length. And when we are writing the alias2 code, we remove the leading one from the binary representation of the number. So for the next 6 bits, we prefix a 1. So we add leading 1 to the next 6 bits to get the binary equivalent of the required number. So n is next 6 bits are 101, 100. To that we add a leading 1. This is the binary number. So what is that in decimal? It is 64 plus 32 plus 8 plus 4 in decimal, which is 108 in decimal. You just have to think of the reverse process of LES2 coding. So for when you're writing the LES2 code of a positive integer, you write the binary form of the integer, and you convert the integer to its binary equivalent, and you prefix that with the binary equivalent of with the alias code 1 of the length of the number. That is, suppose you have a number 4, then the binary equivalent of 4 is 100, which has 3 bits. And this number 3, you go and find the alias 1 code for the number 3, which is 011. And you remove the leading 1 from the binary equivalent of 4. So 100, you remove the leading 1, will be left to 00. And you prefix the alias 1 code of the length 3, which is 011. So you will end up with 01100. That's the alias2 code. That's how you write the alias2 code. So when you are finding the inverse of the uh, code word, then you see the so first part of the code word will be the alias1 code for the length of the binary number. And in the alias1 code, you first see the number of uh, runs of zeros before the leading ones. So you see that there are two zeros. And if there are two zeros, then the next three digits will give you the length of the number. So the next three digits are 111, which is uh, binary. 111 in binary, 7 in decimal. So next 7 bits should be your 7 should be the length of your number in binary. But since you remove the leading one, you have to append the leading one to the next 6 bits. That's all. Then question 5, we did the alias coding. We saw that in question 4 how to do that. But you could apply the idea again. So alias idea for constructing prefix free codes for the positive integers could be could be iterated one more time, resulting in a code B3 of a positive number, which is the smallest n such that B3 is better than B2. That is, L3 of n is less than L2 of n. You could do by trial and error if, I mean, you might think you could do it just by trial and error, but then you will be lost if you actually try to do that. Because B3 doesn't become better than B2 unless you have a huge number. So for quite a few numbers, B2 is still better. So having more iterations will only become better as you are encoding larger and larger numbers. So you will actually have to estimate and compare the lengths of each procedure. So encoding, if you just do binary, then the length is floor of log n plus 1. If you do alias1 coding, then L of n minus 1 zeros followed by b of n is your code. So the length L1 of n is L of n is so it's B of n has L of n bits, and you are adding L of n minus 1 bits, so it's 2 L of n minus 1. But L of n itself is floor of log n plus 1, so L1 of n is 2 L of n plus 2 L of n minus 1, which is 2 times floor of log n base 2, of course, plus 1. Then if you do the next iteration, which is raised to coding, then you have for L of n minus 1 zeros, you do alias 1 coding. Uh, sorry, instead of using L of n minus 1 zeros uh, to tell you the length of the binary number, you do alias 1 coding on the length of the binary number and prefix that. So you do alias 1 coding on the length of n and then concatenate that with the binary equivalent of n. Of course, you have to remove the leading one without leading one. That's alias 2 coding. So in alias 1 coding, you had the binary equivalent, and then to tell you the length of the binary equivalent, you used L of n minus 1 zeros. In alias 2 coding, to tell you the length of the binary equivalent, you use alias 1 coding of the length of the binary equivalent. Then you remove the leading one from the binary equivalent and append that as a suffix. Now, if you find the length L2 of n, it's an iterative procedure. You can work it out yourself, and you will be left with log n, floor of log n plus 2 times floor of log n plus 1 plus 1. So if you iterate one more time after doing alias2 coding, if you want to do alias3 coding, then what do? You do alias2 coding on the length of n, length of the binary equivalent of n, and append that to binary equivalent of n without leading one. So now L3 of n is L2 of L of n plus L of n minus 1. L2 of L of n is L2 of n is floor of log n plus 2 times floor of log n plus 1. So in place of n, you have to replace it by L of n. L of n itself is floor of log n plus 1. So I'll leave that to you as a homework. You'll finally end up with log n plus floor of log of n plus 1 plus 2 times log of floor of floor of log n plus 1 plus 1. We end up with this. Now L3 of n must be less than L2 of n. If so, you substitute for L3 of n and L2 of n in the inequality, some of the terms will cancel out. You will be left with 2 times floor of log of floor of log of floor of log n plus 1. Okay, that is less than floor of log of floor of log n plus 1. You check this. One point to note is that the options are all powers of 2. I have not given you the options, but the options are there in this question. They're all powers of 2. So we only need to check for powers of 2. And the powers of 2 that you need to check for are also 1 minus even number. 1 minus a power of 2. So let's check for 2 power 0, 2 power 1, 2 power 4 minus 1, 2 power 3, 2 power 8 minus 1, 2 power 7. I'll call this L1. Call this L. I'll call this L3 and I'll call this L2. And L3 is 0 here, 1, 1, noc25-ee03. Then 4445, 4667. At this point, L3 is less than L2, which means this L3, capital L3 is less than capital L2 of n. So that means B3 of n is better than B2 of n. I'll go to the washroom for 5 minutes and come back. And then we'll cover the remaining questions. Question 6. Binary erasure channel with erasure probability epsilon equals 0.3. The channel capacity is given by solution from class. We know that capacity of a BEC is C is equal to 1 minus epsilon. Epsilon is equal to 0.3, therefore capacity is 1 minus 0.3, which is 0.7. Question 7. Consider a binary symmetric channel with crossover probability P is equal to 0.4. The channel capacity is given by so BSC is like this. Zero goes to zero with probability 1 minus P, zero goes to 1 with probability P, 1 goes to 0 with probability P, and 1 goes to 1 with probability 1 minus P. So summation of Pj log Pj, J in capital J, J is equal to 1 to capital J. The capital J is number of outputs, is P log P plus 1 minus P log 1 minus P. And since BSC is strongly symmetric, we have capacity is log capital J plus summation Pj log Pj is equal to 1 to capital J, which is log 2 base 2 plus P log P plus 1 minus P log 1 minus P, which is 1 plus P in this case is 0.4 log 0.4 plus 0.6 log 0.6. And if you calculate that, you will get 0.03 bits. That's because log of 0.4 and 0.6 are less than 1, so log of those quantities will be negative. So you are subtracting zero point 0.4 times log point 0.4, zero point 0.4 times some negative number, and zero point 0.6 times some other negative number from 1. So the capacity is less than. Question 8. For the channel given below, for epsilon equals delta equals 0.2, what is the capacity? The channel is as follows. K is equal to 2, so there are two inputs, and J is equal to 3. J out 3 outputs. Outputs are 0, delta, and 1. So 0 goes to 0, priority 1 minus epsilon minus delta goes to capital delta, priority small delta goes to 1 with priority epsilon. 1 goes to 0 with priority epsilon, goes to capital delta with priority small delta, and goes to 1 with priority 1 minus epsilon minus delta. So it's uniformly dispersive. It's not uniformly focusing. You could split it into two strongly symmetric channels. One has the output 0, 1, the other has outputs delta. So you decompose the channel into two as follows. Priority Q1, you go to the first channel, and with priority Q2, you go to the second channel. The first channel, you go to 0 goes to 0 with priority 1 minus X, and goes to 1 with priority X. Similarly, it goes to priority 1 goes to 1 with priority 1 minus X, and goes to 0 with priority X. In the second channel, both of them go to delta with priority Y. Now we need Q1 into 1 minus X is equal to 1 minus epsilon minus delta, and Q1x is equal to epsilon. So Q1 is 1 minus delta, X is epsilon over 1 minus delta. I just substituted Q1x here. Now in the second channel, Q2y Q2 is 1 minus Q1, So it's delta and q2y equals delta. So y equals 1. Now C1 is it's a binary symmetric channel with parameter epsilon over 1 minus delta. A second channel, there's no uncertainty at all. Capacity, there's no mutual information because both outputs go to let's see, both inputs go to the same output. Capacity is 0. That is h of y given x is equal to h of y because y is independent of x. Therefore, h of y minus h of y given x is 0. So, regardless of p of x, I of xy is 0 in the second channel. Therefore, the capacity of this binary symmetric erasure channel is C3 equals summation qi ci, which is q1 c1 plus q2 c2. Q1 is 1 minus delta, C1 is 1 minus h of epsilon over 1 minus delta, Q2 is delta, and C2 is 0. So you're left with here delta was zero point 0.2. So this is 0.8 into 1 minus h of 0.2 by 0.8 1 over 4, which will turn out to be 0.15 bits per use. Question 9. What is the channel capacity of the following DMC? A probability that z equals 0 is equal to probability that z equals 1 is half. Cryptex is 0, 1. Assume that z is independent of x. X can take two values, z can take two values, x and z can take four different combinations 0, 0, 0, 1, 1, 0, 1, 1. And this is not binary addition, this is just normal addition. So I can take 0, 1, 2, 3 values. Probability that y is equal to 0 given x is equal to 0. is the probability that z is equal to 0, which is half. Probability that y is equal to 1 given x is equal to 0 is the probability that z is equal to 1. Which is also half. Similarly, probability that y is equal to 1 given x is equal to 1 is probability that z equals 0 equals half, and probability that y equals uh, 2 given x equals 1, the probability that z equals 1 equals half. Of course, these hold only because x and z are independent. In actuality, this should have been p of y equals 0 given x equals 0 is p of z equals 0 given x equals 0. But since z and x are independent, this turns out to be p of z equals 0. So we can write the channel as follows. So 0 y equals 0 given x equals 0, half, and this is half, and this is half. Therefore, the channel is basically the binary erasure channel with the parameter epsilon equals half and capacity of the binary erasure channel is 1 minus epsilon, which is also half bits per use. Final question, given that, sorry, what is the channel capacity of the discrete memoryless channel where output y is x or z, x is input, z is noise, where probability that z equals 0 is equal to probability that z equals 1 equals half. Script x is 0, 1. Z is independent of x. Similar to the previous problem, x and z can take four different values, but y now is x is z, so it's 0, 1, 1, 0. It can take only two values. And the transition probabilities are p of y equals 0 given x equals 0 is probability that z is equal to 0 is half. P of y equals 1 given x equals 0 is probability that z equals 1, which is half. Similarly, probability that y is equal to 0 given x equals 1 is the probability that z equals 1, which is half. And probability that y is equal to 1 given x equals 1 is probability that z is equal to 0, which is half. The channel is as follows. Therefore, the channel is basically the binary symmetric channel with crossover probability p equals half and capacity c equals 1 minus h of p, 1 minus h of half. H of half is 1, so it's 0. That is, you actually don't convey any information because each of the outcomes is equally likely. So, given observing that you have, if you observe a 0 at the output, then there is absolutely no information. You can't gain any information about whether your input was 0 or 1. That's because it's equally likely that your input was 0 and your input was 1 given that your output is 0. P of x equals 0 given y equals 0 is equal to P of x equals 1 given y equals 0. So, uh, in other words, y is independent of x. Therefore, h of y given x is equal to h of y. Therefore, I of xy is 0, regardless of the distribution of x. That's why the capacity is 0. That is, by observing the output y, you gain no extra information about x. And with that, we are done with the problem solving session for week 5. Next week, we'll cover the topics jointly typical sequences and noisy channel coding theorem and differential entropy.